Can you see the screen?
Yes, we can see.
Yeah. So hi, I'm Kyung Kim, and today I will tell you about using Q components for parametric design in Qiskit-Metal. And before I tell you about some Q components or Qiskit-Metal things, I think it's better for you or me to share some backgrounds about me related to Qiskit-Metal. So I'm Qiskit Advocate from 2021, and I'm an undergraduate student at Seoul National University, majoring in physics and computational science. I'm currently research about quantum dot qubit hardware simulation and machine learning adapted control of quantum dot qubit, and it is quite different with superconducting qubit, even they are or qubits, but so I started Qiskit-Metal almost 1 year ago at first Qiskit Hackathon Korea. At the time, the Qiskit-Metal was not public, so almost every members in our challenge team was newbie on Qiskit-Metals. But we started it from the first day of the challenge, but we successfully solved the challenge problems, which means the Qiskit Metal is not a hard thing to study or hard thing to equip yourself. So what I want to say is, e even if you are very new in Qiskit Metal, you will solve you can solve problems in challenge very easily, or if you study hard about it. So don't afraid and let's start. Before I tell you about some features in Qiskit-Metal, I think many of you are not that familiar with Transmon qubit or related physics about it. So I will tell you some basics about it first. So the Transmon qubit circuit is two main features in Transmon qubit circuit is Transmon Pocket and transmission line. So Transmon Pocket is have a lower of qubit, and transmission line is will connect the qubits or the connect qubit and some readout uh, tips. And one thing I want to remark here is in transmit qubit circuit, most of the surface of substrate is covered by thin matter, which is called ground matter plate. So if you want to add some component in the circuit, you have to subtract some metal plate first, and then you can add some features in there. I will tell you about more detailed things in later with Jupyter Notebook. Uh, so the first key feature in Transmon qubit circuit is Transmon Pocket, which is kind of qubit in the system, and in superconducting qubit, the ratio between Josephson junction energy, and conduct capacitance energy is very important because it determines the unharmonicity of the superconducting qubit. The unharmonicity of superconducting qubit is difference between energy difference of ground state and first excited state, and second excited state. So if the unharmonicity is too small, then two energy gap in superconducting qubit is so small, which means we cannot control the qubit properly. So the junction energy and capacitance energy ratio is very important, and the easier way to control that ratio is control capacitance energy, which can be modified by change the capacitance of the system, and we can change the capacitance of the system by changing its geometry. So in the figure, it shows some geometrical parameters in the Transmon Pocket. such as pad width, inductor width, pad height, or pocket width, pocket height. So by changing these parameters, we can adjust the unharmonicity of the qubit and the energy level between uh, two level system. If you want to know more details about superconducting qubit or Transmon qubit, I share some two good introductory references here. So with these references, I think you can get some basic physics about Transmon qubit and the historical background of Transmon qubit. And about transmission line, usually transmission line is physically implemented by coplanar waveguide, and they are capacitively connected to the qubits or other coplanar waveguides. So in the coplanar waveguide, the resonance frequency is very important to prevent crosstalks, which so to adjust the resonant frequency of CPW, we can modulate the geometrical features such as length and width and gap in CPW. And mostly the main parameter is length of CPW. So if you want to change the resonant frequency, uh, I think the easiest way is changing the length of the CPW. But in both in transmission line and transmon qubit, there are so many geometrical parameters, and it is quite hard to modify them in with only with our hands. So how can we control all of these parameters? The answer is Qiskit-Metal, and it gives a lot of functions which makes we can modify the parameters very easy. So let's see some Jupyter Notebook demonstration. So I prepared some Jupyter Notebook for our today's study, and most of them are part of the documentation in Qiskit-Metal, but I will share this notebook after the study. I have to include add some documentations and references. So yeah, I will share it later. So if you install the Qiskit-Metal properly, then you can import it. Oh, sorry. Yep. So the Qiskit-Metal imported successfully, and let's first set up planar design and GUI for the Qiskit-Metal. So the design is key features in Qiskit-Metal and is connected to GUI. So if we change some parameters in design or components in design, then we can see it on GUI. So if you run this cell, we can start Qiskit-Metal GUI with nothing here. And before I start, before I telling you about some how can we modify some parameters or add Q components in with Python code, I will first tell you about how can we add some features only with GUI. So if you click this circuit image, then you can see libraries about some components. And if you want to add some Transmon Pocket, the only thing you have to do is just click it and create. Then you can make Transmon Pocket here very easily. And if you want to change some parameters here, then you can go to this Q Components tab and click it. And by using right click here, you can rename the Transmon Pocket like Q1. And if you want to change the position of qubit, then you can change values here. And one thing you have to remember is the numbers in this figure tab is the unit of length is millimeter, not micrometer. So if you change some features here, you have to remember that you can change here with value. You can change this value with some arbitrary unit you want. So if I want to change 1 millimeter, then only thing you have to do is write 1 millimeter here. Then it shifted 1 millimeter in the figure. Also, in orientation, you have to remember that the unit of orientation is degree, not radian. So if you enter 30 in here, then we can see the uh, chip chip is rotated 30 degrees from the x-axis. Also, for geometrical features, if you change pad gap to 100 micrometer, then you can see the gap between two pads is 1 micrometer now. And one very useful thing in the Qiskit-Metal GUI is if you click here, you can see the coordinate of that point. And if you click here and here, if you click 2 points, then we can see the coordinate difference from the first click to last click. So if you want to measure something, I think it is the most convenient way to see the uh, geometrical values in here. So if you want to change some parameters in GUI, so again, the only thing you have to do is just changing parameters here, but you have to write unit of the value. Oh, sorry. Okay. So now I will tell you about how can we create some Q components with Python code. So before that, I will tell you how to delete components in GUI or design. So I told you that our components in Qiskit-Metal are saved in the design value variable. So if you run the method in delete our components in design, then you can delete our previous components with this method. So if we have some thing like this in here, and if we run design delete our components and rebuild GUI, then we can see our components are disappeared in the GUI. So how can we add Transmon qubit in with Python code? The first thing you have to do is import Transmon Pocket in here. So this library have some prototypes of each qubit. So if you want to add some other kind of qubit, then you can find that qubit in the documentation. So in this lecture, I will only cover about the transform qubit, not other type of qubit, because in the video which we will see tomorrow, I think it contains some other features and how to create some custom shapes. So in this lecture, I will tell you only about the transform qubits. So the creating Transmon Pocket is very easy. The only thing you have to do is just uh, create some instance of the Transmon Pocket like this. So if you run this, we can see some basic Transmon Pocket in GUI now. in the mm, instance of the Transmon Pocket is if you just run this variable, then you can see the some options and name of the Transmon Pocket. Here we generate it, and the geometrical parameters are saved in QGeometry table. So if you run this code, we can see the polygon object of the polygon object of our Transmon Pocket is saved like this. So this return value is basically the pandas table. So if you're familiar with pandas, then I think you can easily get some values from here. So for example, if I run this one, then we can get first row of the uh, polygon geometry table. And if you get geometry column of this row, then it calls the shapely instance of the related geometry. So shapely is a Python module, and which is very easy. So if you search some materials, then I think you can easily get some knowledge about that. Also, we can get some geometrical table about paths, but we didn't add any transmission line now, so there's no path in our geometry. So then in GUI, if we want to change some parameters here, the only thing we have to do is changing the values here. In Python code, which is very similar to GUI, because it's very easy. So if you want to change the parameters in option, as I told you, if you run this cell, you can get some informations about our current Transmon Pocket. So if you want to change it the position X, then the only thing you have to do is just modify that value like this. So Q1's options position X to 2.0 millimeter, and also change position Y to 2.0 millimeter, and change pad height and pad width. Then if we run this code, then we can see mm, we have to rebuild GUI before to check our result in GUI. So if we run GUI here, yep, we can see the position is changed from 0.0 to 2.2 like this. And we also can see pad height and pad width are changed. Yeah. So then now I will tell you about how can we copy Q components. So in many cases, we will use same geometric or one Transmon Pocket to make any large number of large number of qubits. So if you want to copy some Q component, the syntax for that is very easy. So you can, if you run this copy Q components method, and the first input is the target, and second input is the name of copied component. So if you run this, we can see copied Transmon Pocket is located here. It have position at X position at -2 millimeter is because I set the position of it to -2 millimeter. Also, if you want to copy multiple Q components in same time, you can call copy multiple Q components method, and same with the copy Q components. The first input is target qubits, and second input is uh, the copied Q component's name, and you can in this cell I changed some parameters about Q2 like this separated line, but in we can do that in one line. So if we add some options dictionary about copied qubit like this, then it will generate it will copy it with some changed options. So we can generate a large number of qubits very easily with these copy methods. And also, as I told you, the transmission lines are connected to qubit with capacitance way, with capacitance. So if you want to connect, uh, connect transmission line and transmon qubit or uh, qubit, then you have to make some connecting path. So with this method, we can clean the view in GUI, and it is same in here, but I think you can remember that uh, in previous case we only create Transmon Pocket with this syntax, but you can also create Transmon Pocket with its options. So if you uh, make input option like with dictionary like this, then you can create transform pocket with this option. And also in option, you can create some connection path which have role in make creating connection between qubit and some transmission line. And the list of connection path is also in dictionary. And so if you want to create a connection path in the right and upper side, then you can write this syntax to create the connection path in right and upper side. And if you change the location LOCW in here to -1, then you can create connection path in left and upper side of the transmon pocket. And in same way, if the location W is +1 and location H is -1, then you can create the right and lower side. And in this case, we can create a connection path in left and lower side. Also, you can set pad height or pad width of the connection pad with this input. So the connection paths are rectangular shapes, so it has height and width. And if we want to modify that value with default value, then we can add the parameters like this. And if you don't add this kind of parameters in the connection path dictionary, then it automatically set those parameters with default value. So if we run this cell, we can create Transmon Pocket with 4 connection paths. So we create upper right side connection path with default value like this, and we created left and upper side with some modified path height. So if we zoom in, just a moment. So default height is 30 micrometer. So let's see connection path C. So in connection path C is located on the right and lower side, and it has large width. Let's check. And in the right and lower side, we can see the pad width is larger than default value. And for the connection pad D, which is located on the left and lower side, we can see its height is larger than default value. So we can very easily change the geometrical parameters of connection pad 2 with Qiskit-Metal syntax. And also, usually these options are very wrong. So we can, in most of Qiskit-Metal documentation, they usually create a dictionary variable of options like this first, and then use these options to uh, like this. So with this syntax, Python syntax, we can merge two dictionaries. So if we run this cell, we can create 3 Transmon pockets in our GUI with each of the Transmon qubit have its connection path. The other thing in the quantum in superconducting qubit circuit is transmission line, and I told you that the length of the transmission line is very important. So if the distance of two pinpoint is short and our required transmission line length is long, then we have to make them curved to compress the area which the transmission line is occupied. So for that, we can use root minder object in Qiskit-Metal, Q library, T lines, and minder. And if we see the template option here, then this is the default options for the transmission lines. And this thing is important because if you want to change some parameters, then you can refer this first. So if you want to connect to superconducting qubit, it is very simple. First, we have to define the options dictionary, which is so in coplanar waveguide there's some geometrical parameters like is total length and is where the transmission line start and where the transmission line end, and how long how long to the length of the start point with straight line and the length of straight line in the end point. We will see these parameters later. So if you add CPW line with this syntax, then you can connect Q1's A point and Q2's B point. So Q1's A point is here and Q2's B point is here, and the length of this line will be 8 millimeter. And if you see here, there's some troubles in here because the coplanar waveguide also passing the C point of the Q1, so we have to change some geometrical values here. To that, we can change the parameter, the start straight here. So if you change this parameter, then it goes straight for few lengths, about 100 micrometer, and then uh, it will automatically determine the shape of the transmission line. So if we run this cell, we can see there's some straight line here, and these curves are generated with the parameter here, fillet. So if we set the fillet radius so more smaller, we have to change it here. with smaller radius, then we can see the fillet radius is more smaller in here. Uh, in same way, we can connect Q2 and Q3, and also we can connect Q2 and Q3 with other transmission line like this. Also, we can set some parameters in transmission line. So if you want to customize jokes in the transmission line, then you can set some point like this. So this means that the transmission line will be turned left after it goes 800 micrometer, and then it will turn left, and after it goes 500 micrometers straightly. So if you run this cell, we can check this the result of this code in here, and it says it turn left after 800 micrometer straight line, so it turns left after go 800 micrometer. Start from here, it goes 800 micrometer and turn left, and also in after 500 meter go straight and turn left. So you can see the result of this code in here. And also, but it is quite hard to set these parameters to make the coplanar waveguide to pass the point where we want. So we also can set the anchors. So let's start with this 2-qubit system. And if we set anchors in here, anchors like this, so you can add this point and this point and this point as an anchor, then you can see the transition line pass through this point and this point and this point like this. The transmission not actually pass this point because of the fillet, but it almost passed the anchors. So also with this generated design, we can check the polygon geometric objects with same syntax, so which I showed you before. And now we have transmission line, so we also have some path objects in the geometric table. And in geometric table, one thing I want to remark is there's some column which is subtract, and as I told you in the slide, to add some features in superconducting circuit, superconducting qubit circuit, you have to subtract the ground metal plate first. So this rect pk object is about this area where the Transmon pocket will locate. You can also check the where to subtract and where to create geometry in GUI2. So in gray area, like here and here, is the place where the ground metal plate should be subtracted, and the blue area like this means that there is some object we want to put is located. So this is all I prepared, and as I told you, I will upload this notebook in Slack channel, so feel free to run this code and play with it. So thanks for listening.
Thank you, Kyunghoon, for preparing the lecture and materials. I look forward to try your lab material soon. And for the rest of the time, let's watch the fourth lecture of Qiskit-Metal lecture, which edited it for about 40 minutes. If you have any questions during the lecture, please leave them in the chat and I will organize them and post it